So my name is Sarah Saltzer. I'm the Managing Director of the Stanford Center for Carbon Storage. And I am so pleased today to be here at the Scaling Sustainability Innovation, but particularly for this startup showcase on carbon management. So we basically have a little under 90 minutes to hear from some startups in this area. So, the carbon management landscape actually has quite a bit going on in it. I really like this graphic that was put together by Precourt's Understand Energy, which is actually a course that's taught here at Stanford. And they have this picture on their website, so I stole it. But it really does a nice job of laying out what carbon dioxide removal is, which is taking CO2 out of the atmosphere or oceans. Carbon capture, which is capturing CO2 before it is released from the flue stack. And then in both of these cases, sometimes there's some automatic sequestration that goes on, but sometimes we end up with some gaseous CO2 that gets perhaps put into a pipeline or transported in another means. And then that CO2 can either be stored underground or stored in another way, or it can potentially be utilized. And this is the whole landscape that we're going to be talking about in this session this afternoon. So what we have for you actually is 6 startup companies that are in different parts of this landscape. We're going to hear from GigaClimate, which scales climate innovations into profitable companies. And Nicola is going to talk about their first company, which is Carba, which is a bio-waste to solid carbon solution. We're also going to hear from Carbon Blade. We're going to hear from Callie Marshall. And Carbon Blade combines electrolytic separation, alkaline absorption, and solar or wind energy to create modular, transportable containers that capture and sequester carbon at the source. Then we're going to move into storage. We're going to hear from Isaac Ju from EarthFlow AI, and they have a deep learning modeling suite for CO2 storage. We're going to hear from Anindita Banerjee from Resource Chemical Corp., which works on plastics from CO2 and inedible biomass. Then we're going to hear from Kumiyoko, I got that wrong, really wrong, Yoshinari, from NovoNutrients, who has a fermentation platform using organisms to transform emissions, along with hydrogen and oxygen, into complete, safe, natural single-cell protein ingredients for food and feed. And we're going to hear from Dioxical, which has an electrolyzer technology that tears apart carbon emissions and rebuilds them into energy-rich and useful molecules. And Joshua Rabinowitz will be representing Dioxical. And we have another special thing in this session. So Stanford Door School recently launched a sustainability accelerator. And they also, as part of that, the first focus area of the accelerator is greenhouse gas removal. And that's what that little swirly thing is over to the left. That's like their logo. And we actually have 4 different fellows that are being funded through the accelerator who are going to talk about some of their work as well. So these aren't quite startups. Well, actually, a couple of them might be, but they're like proto-startups. So we're going to hear from Isabella Rios Amador, who's going to talk about some marine carbon removal technology that leverages seawater electrolysis to capture CO2, deacidify the ocean, and generate clean energy. We're going to hear from Peng Zhu, who's going to talk about some similar but different things around electrochemical CO2 removal and ocean alkalinity enhancement. We're going to hear from Zheng, who's going to talk about developing a scalable approach to transforming cement waste recycling through innovative and sustainable technologies. And finally, Divya Chalise, who's going to talk about ultra-low-cost conversion of ag waste biomass into stable, non-decomposing carbon. So we basically have 10 presenters. They're each going to get 6 minutes to basically pitch what their startup or research is doing. And after their 6 minutes, then we'll have 2 minutes for audience Q&A. And then we're going to move on to the next speaker. So given that we have 10 speakers, that's 8 minutes each. And it's already 2:05. We're going to get started right now, but we're going to have to move at a fast clip. So if you do have questions, make sure you have shortened that question down to as short as possible so that we can get the Q and the A both within that 2 minutes. So without any further ado, I would like to introduce Nick Halla, and he will talk about GigaClimate and Carba.
Thank you for being here. I'm going to talk about GigaClimate, which I'm the founder CEO of, and then Carba is the first company that we're building under GigaClimate. So what do we do at GigaClimate? So my background, I've been scaling technologies for quite some time. I'm a chemical engineer. Initially, I worked at General Mills and then came to Stanford to start companies in renewable energy and joined a professor, Pat Brown, who had the idea for Impossible Foods and then built Impossible Foods with him for 11 years. So I left a couple years ago, looked at what I wanted to do, and my dream had always been to create Bell Labs, Edison Labs for climate technologies, sustainable technologies that could change the way the world operates in a much more sustainable, economical fashion. So what we do at GigaClimate is we're targeting companies and ideas that have billion-person, gigaton scale impact and really driven behind fundamental economics at work with a very strong climate attribute behind it with the impact in the greenhouse gas removal. What we do is we find technologies that have something that's at least ready to start moving off the lab bench into a pilot or a commercial enterprise. And then we embed our people into the company to take it from that stage to a fast-moving growth company with the team, technology, business model, partnerships all behind it. So we'll come into a place like this, talk to a bunch of scientists and see what they're working on. We work with accelerators or Activate, if you're familiar with that platform that helps fund scientists commercialize their technology. I was just at ARPA-E recently. And when we find teams that have something that we think can actually turn into a really strong economical business with a big climate attribute, then we embed our people into the company to build it between commercial, finance and fundraising, people, a lot of recruiting as we build the team, and get it to the place where it's on its own. And then once we have that, we back out and move towards the board role. So with that, we have three main areas that we've started focusing on. It started with the ethos that 95 to 98% of the money going into climate goes into decarbonization and industry transformation, like Impossible Foods. But we need to do a lot more on adaptation resilience. Climate is changing. We need to manage it and starting to undo all the negative stuff we've done, methane, nitrous oxide, carbon capture, to really try to catch up to what we've done to the world. All massive opportunities in all these fields. And then as we got into that, we started looking at the biological carbon removal space under the thesis that if you are going to remove carbon at scale, biology is already doing a lot of it. And that led to Carba. So Carba, we transform biological waste into profitable biocarbon. And there's a few things that we can do with this. We put together a team. I met the two founders, Andrew Jones and Paul Dwanhauer. I actually had taught at Paul's class, and so I knew him before. And they had an idea for how to do this at scale, very economically. Started partnering with them, and then since then we've just recently hired a COO who's scaled a bunch of early stage technologies and our head of commercial who's been in the carbon world for about a decade. What we do is we take biomass, woody biomass waste in the first project. We designed a new way to very cheaply, autothermally turn it into biocarbon with a 60 to 80% carbon yield, very high compared to what normally would be in the biochar industry. And then we can use that either in materials to replace carbon materials. We can bury it for pollution control and 1,000-year per minute carbon removal, or use it for biochar in soil amendments when the value is there. In the US, those are all three very big opportunities. We're starting with the top, which is burial and pollution control, which will go into a project. We have some early research we're starting to do in carbon materials. And then, like we talked about, the more traditional one in this is biochar and soils, which we've done a little less in today. So how do we do it? This is a kind of mock-up of the reactor that's being built right now, 60 to 80% carbon yield. We do this by keeping the reaction temperature lower. We found a way we can drive a lot of heat and temperature, essentially heat transfer into the material quickly to essentially make slow pyrolysis fast. Each system's about 10,000 tons of CO2e per year. It's autothermal. We can take a pretty wide range of feedstocks the way it's designed so that we can take any waste negative value feedstock. And then with that, we've worked with Isometric to build a 1,000-year permanent burial methodology, which we published in February, how to get very high permanence, high credibility carbon credits behind it. So with the first project, we are working with a very large landfill operator. And so what we do is the biomass is already there. We're not shipping it. That kills a lot of biomass projects. We take that biomass instead of composting it, which releases a lot of CO2 and methane, and is also a big operational management issue for the waste handler. We turn it into biocarbon, and this landfill is also required to do a cover layer on the trash every day to keep the pollution in, which is normally dirt. Instead, we're putting the biocarbon in, which essentially turns the landfill into a carbon filter, like a Brita filter, to entrap PFAS and toxins and trap those in the landfill and clean the leachate. while being a very low oxygen environment with very low degradation potential for the carbon. We have a commercial contract we just signed with Microsoft for 44,000 tons of offtake over 5 years. This is a highly replicable. With this landfill operator, there's 130 plus sites with this operator that we think we can scale this technology in. We were selected for a DOE grant to build it out, and we got some PRI funding from a couple foundations. And we talked a little bit about the co-benefits. So example, methane, you can reduce methane production in the compost. You can reduce methane reduction in the landfill too. Biocarbon or biochar is known to be good housing for methanotrophs, which eat methane. And you can trap toxins in. These are all long-term, more monetizable, not in the short term. Short term, the monetization is the biomass coming in has a negative value, and we have the carbon credits on the back end. So in the last 9 months with the company, we've signed that 44,000 ton offtake with Microsoft. We've finished the 1,000-year permanent protocol with Isometric. We have a collaboration agreement we're operationalizing with the landfill partner, along with the funding and hiring the team. And so we've gone from 2 people in December last year. Now we're up to about a 12-person team that is going to be full-scale commercial by end of this year. So that's it.
Awesome. Great.
I think right on time. Perfect.
Questions for Nick?
Yeah, it's a good question. We built the company on a few different commercialization paths because that is definitely a risk on where that goes. Voluntary carbon markets are there. If you look at the purchases in durable carbon in the last 5 years, every year is a significant uptake in how many durable carbon credits have been purchased because buyers are looking for more stability in that market compared to the more traditional forestry type credits. We do predict this to go up. Biochar and this type of solution is likely going to get adopted into the compliance market in Europe, which also is another whole lever there. We've talked to a bunch of companies looking at doing their own internal work. And so we could just sell our systems, license it out for them to reduce their own emissions. So you don't even play in the carbon markets. And I think in this space, you have to have different business models like that because the straight voluntary market is still very TBD.
One other question over there.
Yep.
How much of your daily
Yeah, so this system would be about 30 tons of dry biomass per day.
using dry
Dry biomass, yeah. Yep, so the way we're designing this, you don't want to have to pay to dry water off, so we do it a very efficient way to dry water off. You can just use sun, obviously, and if not, you can just use a dryer. And then you essentially process it through here. So dry-ish, not fully dry, but dry-ish. Yep.
Could you tell us a little bit about the feedstock for pyrolysis and
Yep.
sourcing it and scaling that?
Yeah, so we specifically put the first site in the Minneapolis area, the Twin Cities area. There's about 600 to 700,000 tons of waste woody biomass there every year, just due to tree trimming, storms, and there's a big emerald ash borer disease ripping through. And so it's been going up quite a bit, and they don't know what to do with it. And so a lot of it just gets burned right now. Some gets used in an energy facility, but it's very uneconomical, so they're trying to figure out. So we could do in this Twin Cities area, several 100,000 tons relatively easily. But just with that one. Now we can take corn stover, we could take grasses, we could take all kinds of stuff. We've talked to a bunch of food waste companies too.
So, okay, if you have more questions for Nick, you can find him after this event.
That's good. Thank you.
Okay, thank you, everyone. Isabella. Maya?
Awesome. Hello, everybody. I'm going to be talking about sinking carbon and saving seas while we're at it. I'm a PhD candidate here at Stanford in the Chemical Engineering Department and in the SLAC National Lab. And through the Accelerator Program for Greenhouse Gas Removal in the Dorr School of Sustainability, we've been developing this technology that we believe to be scalable, economical, and sustainable. Here you can see the list of my team members. They're incredible. Some of them are here in this room, and I have the pleasure of working with them. Before I go into the tech, I want to tell you a little bit of where this idea came from. I studied marine science, and about 7 years ago, I founded this nonprofit called Coralisma that is dedicated to the restoration of coral reefs. We do exactly what you see here in the board. We save, grow, and then restore coral reefs back into the Mesoamerican reef. We've planted over 3,500 corals, a number that we've doubled in the last 2 years. Here you can see a very happy face of mine with a fast-growing coral that's about to get restored onto the reef. So while I was doing all this, studying marine science and all, I spent a lot of time thinking about ocean water. Ocean water has a lot of stuff in it. It's not just water. It covers a vast portion of our Earth, about 71% of the Earth's crust. And so it's an untapped resource that we could use. It has a lot of minerals that could be very valuable, but it also has gases like CO2. And so if you were to compare the atmospheric CO2 concentrations to the oceanic concentrations, you'll realize that if you measure it per volume, it's about 140 times more CO2 in ocean water than the atmosphere. This becomes really important when you realize that a lot of the technologies around carbon capture are the most limited energetically intensive step are concentrating that carbon from the atmosphere specifically, like direct air capture. And so since the ocean already did this step, we can really take advantage and remove the carbon directly from the seawater. This space has gained a lot of attention. There are technologies that range from more bio-based, like farming kelp and trying to capture the carbon through that, to more tech-heavy designs and systems like ours. So we fall on this last panel, direct ocean capture. We actually don't love to use that term because technically the ocean already did the capturing for us. We're just converting it and removing it. Our technology can be considered an all-in-one. We have 3 reactors, 1 energy storage unit, and multiple revenue streams that we envision. I'll show it to you and you'll see that it is pretty unconventional. This is because when we were trying to brainstorm a solution to this problem, we came at it from the point of view of trying to make a technology that would be economical, that would pay for itself without the carbon credits. And also a technology that we could plug into other technologies that are already being scaled. This is how our block flow diagram looks. We have these 3 reactors at the heart of it. In the bottom here, we have a seawater electrolyzer. And so this takes in seawater and renewable energy to produce 2 gases, hydrogen gas and chlorine gas. These get stored in tanks. And depending if you want short-term or long-term energy storage, you can size these tanks to that size. And whenever the energy is required, or the renewable energy can't run anymore, let's say the sun is not shining or the wind's not blowing, then we open up these tanks and we feed them into the chlorine fuel cell that will regenerate that energy back into the grid. Now, for the carbon capture component of all of this, so we're not just making 2 gases, we're also making base. The seawater electrolyzer makes sodium hydroxide that then gets mixed with seawater, and this pH swing will precipitate out rocks. These rocks, like calcium carbonate, are the captured carbon. We remove these, and then what's left over is slightly basic seawater that has stripped CO2 from it. This goes back to the environment, helping with marine restoration. There are multiple revenue streams that we see here. And for now, right now, we're at the stage of prototype development. So this summer, we will be building a prototype in Marine Hopkins Station in Monterey Bay. If you've ever been to the Monterey Aquarium, we're right across the street from there. The goal is to utilize real seawater to see the purity of these minerals and assess the market size that relates to them directly. These are our partners. In green, you can see our current partners, some amazing people I've got the pleasure to work with. And then in red, you can see our wish list, the people that we've targeted that we would like to collaborate with. And so at the top here, you can see that we've identified the GSB. We would love to collaborate with a graduate student in business to co-develop our techno-economical analysis and our business model. So if this is of interest to you, please come talk to me, and thank you all for listening to me.
Questions?
Yeah, they're one of the main funders, actually. So they funded the idea when we were first developing it, and they have a fellow that works in our lab, in the Jaramillo lab, actually, that helps design the techno-economical side of things. Absolutely. I think the largest concern stability-wise is within the membrane electrode assembly once you're making the precipitates. And so the short answer is the precipitates could occur inside the device instead of outside the device. We're currently testing some technologies to make sure that the flow gets rid of those precipitates where we want them to be.
Okay, great. Thank you so much. Okay. Okay, our next speaker is Callie Marshall from Carbon Blade.
Well, good afternoon. I'm Callie Marshall. I'm the CEO of Carbon Blade. I'm an alumni from the Industrial Engineering Department, although now it's been assimilated into the MS&E department. I'm also an alumni of the Stanford GSB, well before the beautiful Knight Center even was contemplated. So, but I still feel like it was just yesterday that I was a student here. Carbon Blade is a clean tech company based in San Diego with a mission to combat climate change by delivering low-cost, self-contained carbon removal solutions in a model that they can be very broadly deployed in such a way that they can be co-located with a place for carbon utilization or sequestration. The problem we're addressing, as I think is quite familiar here to many folks here, is that in order for us to have any chance of mitigating the continued climate changes, we need to have solutions at massive scale to remove CO2 from the atmosphere. And while there's many excellent initiatives going on around direct air capture, the majority of them are using technologies that require really extensive amounts of electricity and or heat, and really constrain where they can be deployed based on access to cheap energy or other infrastructure factors. The way that Carbon Blade attacks this problem is that at the core we have a technology that's our Captus technology, which is an electrochemical process that is a very low energy method that operates at ambient conditions using a pH swing method to control the carbon. So some clear similarities with the marine CDR we just listened to. The energy needed to capture and then in a controlled fashion release the carbon is low enough so that at material scale, this can be powered with dedicated onboard renewable energy, a combination of wind and solar. The process also is a closed loop process for regenerating the solvents. So this can be completely independent from any infrastructure and self-contained and basically dropped in wherever there's a need for it or an economic use for it. So we can eliminate transportation of carbon and we can basically bring the carbon capture and the carbon source to all the places that may want to use it or sequester it. We envision great modularity for our approach here. So we have the economics that we've set up is that we have for a capex of about 200K or less than 200K and an operating cost at about $100 a ton. We can economically have a unit do 1 ton a day or 350 tons a day at economics that are basically an order of magnitude lower per ton than the largest installations to date. In the interest of time, I'm going to go quickly through this. The core of the technology is that we expose a base to the CO2 that's highly reactive, that forms a soda. And when we introduce acid to the soda, it releases the CO2 in a controlled fashion. And now we can make that available for sequestration, mineralization, as feedstock for value-added materials like building materials or synthetic fuels or others, or direct use of the gas for greenhouses, for biological yield boosting, or in food and beverage. And then the remaining salt, we process through an electrodialysis, and we regenerate the acid in the base and make it ready for the next batch. Our core unit is the Captus CR1, which is a containerized unit with its own dedicated power generation from solar and wind. It's a passive air capture system that has liquid solvent of the base, running through many, many blades to maximize the surface area that interacts with the air. And then inside, we have the Captus system that processes it. We have a close collaboration with the UC San Diego Energy and Carbon Institute. And so we're building a pilot there together. You can see the San Diego trolley. And so we're about 2 months away from being operational there. And this year will be targeted to do about 1/10 of the core unit that we have. The market that we're targeting, we believe, is massive, because we will deliver carbon into sequestration, into feedstock and value-added gas. And the forecasts vary greatly, but I think all the analysts agree that it's in aggregate something that's growing at a very high clip. Expecting about 28 billion by 2030, growing at 15% beyond that. Our business model has really two main sides to it, where we sell the CO2 as feedstock and as value-added gas. We aim to deliver that as CO2 as a service. So we place the equipment and we charge per volume of CO2. But we can also place it and participate in the carbon offset market. So obviously tax credits available, but our model is not dependent on it. We hop through. So the team that we have is really a team of industry veterans across a broad set of areas: carbon management, chemistry, geology, clean energy, new business creation, and business scaling. In closing, want to share kind of a vision here that we don't see a reason why we couldn't have carbon capture really happening everywhere. Yes, we should still have a big centralized implementations like on Iceland where there's cheap heat, but we really can enable something that can be broadly distributed and for many different purposes. And as I shared before, the economics here that we're looking at, that we believe we have good line of sight to, really are an order of magnitude lower than what some of the amine-based systems are doing today. So we're looking, we're in the process of looking for partners to help us accelerate this journey.
Awesome. Great. Thank you so much, Howard. Questions?
So a very good setup, because I forgot to use my prop. So here is a brick that's made with CO2 and calcium oxide. This is what our researchers at UCSD will be making from the pilot. So really building materials and contributing into a carbon that's as aggregates is by far the largest opportunity. It'll take some time to penetrate that marketplace. Therefore, something like greenhouses actually is in the early area that we're going to go, because we just need to deliver gas basically and replace the existing source. But it's building materials is what we view as that's going to be the largest market in a 5-10 year time frame.
Awesome. Okay. I think we're out of time, unfortunately, but
Okay.
why don't you two meet up?
All right.
And
Thank
our
you.
next speaker, thank you so much. Our next speaker is Peng Zhu from the Greenhouse Gas Accelerator.
In chemical engineering department, the same, and my advisor is the same as like Isa. Tom Harmir is my advisor. So although we are dealing with the same seawater, but what we did is like trying to find different narratives to solve the same problem. So you may be familiar with the background, the CO2 emission problem, but what I want to address here is like there's still a big gap between current existing CO2 removal methods. So we can see in the right side, there's still like in 2030, there's still 1 gigatons CO2 should be removed by using some kind of novel CO2 removal technologies. So that what we want to do is try to address this kind of gap between current scenarios and the proposed levels of carbon removal. So why we want like do ocean, like seawater electrolysis, like seawater alkalinity enhancement? We can see like in the last few decades, like some investments have been launched into different CO2 removal technology, such as the green part, which is the forestry-based technology, and the red part and the purple part is like the bio-based or some like direct air capture-based technologies. However, for some like novel technology, especially for like ocean activity enhancement, the abbreviation is OEAE. This kind of technology is kind of like have a great potential to capture CO2 because like what ESA introduced, it has a higher concentration of CO2, and every year it can absorb like 1/3 of the annually generated CO2. So that makes a great candidate for the CO2 removal, but there's still a lack of like investment for this kind of technology. So that's why we want to do, and what we want to do is like to enhance the capacities by utilizing the seawater. So what's the problem and what's the technical challenges here? So we know like in traditional seawater electrolysis, so if we want to make sure our whole system run for a long time, there's some kind of like these two challenges hinder the like lifetime of our system. So one is the case of precipitation. So we can see the left side, like the left side, the pie figures. So in the seawater, we have a lot of like calcium or magnesium existing in the seawater. So once we're doing the electrolysis in our system, we can generate a lot of like OH is a high alkaline environment in our cathode side. So this cathode side, the OH minus group will combine with like calcium, magnesium to form the precipitation, which will block our whole reactor and make the reactor fail. And another reason is like we can see in the anode side, we have like a lot of chloride ions existing in the seawater. So it may play the roles as a competing reaction compared with like OER reaction. So this kind of like chloride evolution reactor will erode our electrode to also make our whole system fail. So that's like to address these two challenges. So what I did, like what our team did, is try to utilize the hydrogen elution reaction and hydrogen oxidation reaction, which is kind of like currently well-developed technology. By using this kind of like hydrogen redox into our system, we can minimize the voltage, try to avoid like the chloride evolution our cathode side, our anode side. At the same time, we also have some like innovative like reaction design by replace like traditional one membrane like electrolyzer to two membranes. But this kind of membrane can separate the seawater with our reaction itself, try to avoid like the salt precipitation of our whole system. And you may wonder like if we introduce extra like membrane, it may increase the whole like cell voltage, like the increase the ohmic resistance. So what we did is we have like very thin layer with a very high ion conductive layer. So this kind of layers will ensure that our whole system do not have a very high overpotential compared with the initial like system, but we still can maintain a very good performance and very good like stability during the electrolysis progress. So here is like the whole progress, like overall reaction what we have. So like in summary, so what we did is that we have this real seawater inject in our system and go through our electrolyzer. What we can obtain is like magnesium carbonate, and we can also get a very high purity, high concentration sodium hydroxide and HCl. So the concentration is around like 1 weight% to 5 weight% depending on our like operation conditions. And like this is like some like initial like data for our whole system. So right now in our lab, so what we did is like around like 5 centimeters square electrolyzer. So the daily capacity of daily production rate for our system is around like 1 liter. And right now what we are trying to do is to increase the whole electrolyzer area to like 100 centimeters square. And the production rate is around like 100 liter per high purity 1 weight% sodium hydroxide. And the mostly like we also conducted some techno-economic analysis for the whole system. But right now, if we only consider the whole electrolyzer system, the overall cost to capture CO2 like per ton is around like $200. And in the future, with further optimization of our whole system, we can bring down. We are still on progress for the optimizations. And what we can do, like in the future, we can bring down the overall cost to almost around like $100. And finally, like thanks very much for my team and thanks for Stanford Accelerator cohort to hold my project. And thank you all for your listening. Thank you very much.
Thank you. Questions for Peng?
Oh yeah, right now, so we are also right now we are using commercial PM like Nathan membranes. We also refer to like different membranes like the chloralkali industry membranes. But those kind of membranes not that suitable for our seawater electrolysis progress. But what we did also, you have some like modification and fabricate new membranes, try to make the membrane suitable for our seawater electrolysis progress. Yeah, we have catalyst design, membranes design, and also our react design. Yeah, it's a comprehensive system. So right now, so we already, not for our seawater electrolysis progress, but we have some experience into like carbon dioxide reduction. So we can like easily to transfer our like small scale to large scale. But in the future, we must cooperate with our potential maybe electrolyzer suppliers to try to make like whether it's potential for like large scale, maybe like 1 square centimeter, 1 square meters. But right now, it's still under the kind of lab scale. So, yeah.
Great. Okay, thank you. Thank you so much, Peng. Okay, our next speaker is Isaac Zhu from EarthFlow AI.
Good afternoon. I'm Isaac Zhu. I'm a PhD student from Stanford University and also the co-founder of EarthFlow AI. The energy transition needs subsurface energy projects to reduce hundreds of billions of tons of CO2 by 2050. EarthFlow AI is going to make reservoir simulation cheaper, faster, and safer for all subsurface flow domains through our industry-leading AI-based physics simulations. Our prototype has already been used by industry leaders such as NVIDIA, Chevron, ExxonMobil, and Microsoft. Let me start with where we're focusing first, carbon storage. This is a fast-growing market. It is expected to build more than 5,000 storage projects by 2050 to meet the climate target. As shown here, each storage project needs to go through the life cycle of planning, permitting, operations, monitoring, and also verifications. We can be useful at every those stages with our physics-based simulations. But here's the bottleneck. Traditional simulation tools are expensive. It costs $4 million per project, take 3+ years, and this drastically slows down the CCS and scale up. And also the current industry tools are designed for oil and gas, are not optimal for CCS. We are designed for CCS, but are compatible with legacy oil and gas operations. Our competitor use expensive commercial simulators, which make it very challenging for new players to develop their own project. What if there is a better way to facilitate the energy transition, but at a much cheaper price? That's where we're coming in. We pioneered the AI-based physics simulation in subsurface flow, with our research being cited more than 800 times in just past 3 years. We combine deep domain knowledge with state-of-the-art AI expertise, exactly the skills needed to supercharge this industry. And in order to tackle our beachhead market, CCS, our first prototype, CCSNet, is online, available for everyone to use. If you type ccsnet.ai in your browser, you can experience our technology in real time. So this web app is powered by our AI-based full physics simulator that is 700,000 times faster than incumbent solutions. CCSNet transformed the landscape of subsurface modeling across 3 critical dimensions. First, speed. Traditional simulator takes weeks to run realistic scenario. Our AI-based model delivers results in seconds. Second, cost efficiency. Our platform eliminating complex simulation workflow, which can reduce project costs by 95%. Third, and also most critically, our platform captures uncertainty rigorously through running tens of thousands of possible scenarios thanks to our speed up. And that allows engineers to really understand and also minimize potential risks associated with injection projects. This satellite view actually shows the computed probability of CO2 plume entering different locations in your storage site. Also, I want to highlight what really fundamentally sets us apart from other AI solutions in the space. Most of players are focusing developing highly specialized model. We've taken a more ambitious path. We are building a true general purpose AI-based physics simulations that is based on neural operator trained on massive high-quality data. Once the model is trained, it can take various inputs such as well configurations, different injection design, and give the corresponding dynamics at a lightning speed. Also, the biggest company in the world are already using our demo website. Our beta platform, CCSNet, as this demo shown here, has attracted hundreds of monthly active users who are experts from leading energy companies such as Chevron, ExxonMobil, and also the tech company who have energy initiatives. We have conducted 100 customer discovery call, and we found out the impact of our technology is very evident in the market. And so our go-to-market strategy is like, we start with this free app. This creates a very powerful funnel, allowing potential customer to experience our technology firsthand. And then we identify key players who understand and also appreciate the value of our technology and can be our potential customers. And to this date, we have late-stage conversations with 3 storage developers to integrate our platform into their daily workflow. And the revenue model as shown on the right here evolves in 2 phases. First, we focus on 10 bespoke customers through our engineering consulting. This hands-on approach will allow us to really understand our customers, but also more importantly, generating early revenue. And then when we scale up our system, we're gonna transition to a SaaS platform that really allows people to plug and play. This scalable approach will maintain the strong unit economics. We're projecting we can achieve $50 million by year 5. And the carbon capture market right now is like 50 million tons per year. It's expected to grow to 5 to 10 billion tons a year by 2050. It's 2 orders of magnitude of growth. And however, CCS is just the beginning. We can apply our recipe to any subsurface flow domains, including the emerging markets such as geothermal, lithium brine extractions. We're actually building a commercial expansion of our CCSNet so that we can enter in those exciting adjacent markets. And EarthFlow has the expertise, the edge, and a commitment to the energy transition. Thank you for your attention.
Questions for Isaac?
How did you describe the Amador and how did you share your win the result? Because the oil companies are very secretive about their own results. So how do you do that?
Okay, that's a great question. So we train our model based on the synthetic data generating from the physics-based simulator, and then we'll work with our partners so that we have a base model and then condition on their in-house data.
So with the European AI, already pursued them.
Actually, yeah, there's a quote, it's like all the models are wrong, but some are useful. And that's kind of the philosophy we're holding here. So because subsurface is the challenge with us is really we have only sparse observations. It's a massive uncertainty in terms of geological structures, even physics. But the tools we can use is really the physics-based model. And then we train a model to replicate these physical processes and then condition on the monitoring they have and to give them the decisions they will like. That's what the industry has been doing. So we just try to facilitate that process.
Time for one more question? Yeah.
Go ahead.
Does your methodology have to
The reason why we're name ourselves EarthFlow AI, we kind of definitely that's one of the physical system we're interested in. But so far we care about porous media, which has its own set of governing equations, which is different from oceanic simulation. But we'll be love to expand to those if we have talents. So, but at this point, we still focus on the subsurface energy processes. But the recipe, I believe, is applied the same.
Great. Okay.
Thank you.
So thank you. Another hand for Isaac. Now I would like to introduce Anindita Banerjee from Resource Chemical Corp.
Hi everyone, my name is Anindita Banerjee, co-founder and CEO of Resource. What we are doing at Resource is turning CO2 into breakthrough materials, the first of which is a paradigm-shifting alternative to fossil fuel-derived plastics. Plastics are uniquely versatile. You will find them everywhere, driving innovation. What makes them so special are their properties. So they are moldable, customizable, lightweight, cheap. As a result, 460 megatons of plastic are produced every year. It's a $620 billion market and is only projected to keep growing. However, plastics have a huge impact on the climate and on pollution. So just the production of plastic itself is responsible for over 5% of our total GHG emission. But that's not the only challenge with this industry. The other huge issue is the waste accumulation. So every year, over 250 megaton of plastics get discarded. And with an average lifespan of hundreds of years, they keep accumulating in the landfill and then go on to pollute the environment. And very little of it actually gets recycled. So it's no surprise that governments and businesses, they are seeking for alternatives. But the problem has been that plastics properties are so hard to replicate. You will not find any other material that's available today that can serve the range of functions or applications that plastics serve. So governments, they are working by imposing taxes, plastic end-of-life taxes, putting mandates for sustainable alternatives, and even outright banning single-use plastics. Businesses, they are looking for alternatives that can increase their product shelf life, that can be lightweighted, and that have a superior end-of-life profile. And finally, there's also a clear shift in consumer demand, both generally as well as across critical sectors like, say, cosmetics, where customers are choosing to pay more for, say, a packaging material that they believe has been sustainably sourced over fossil fuel-derived packaging material. Enter Resource Chemical. What we are doing is taking a long heralded plastic alternative called PEF that was patented 70 years ago but wasn't scalable to date. What we have done is we have developed a patent-protected process to drive its scale and cost efficiency. So just like your regular plastic, it's moldable, customizable, lightweight, and can also be made to be cheap. But in addition to that, you can make it carbon negative, depending on your tech. It results in zero waste. It's recyclable using existing infrastructure, and it can increase the shelf life of the product packaged in this material, reducing product waste, for example, food waste. But despite these advantages, PEF actually never got commercialized. And the reason for that is the building block of PEF, that's called FDCA. No one was able to make FDCA scalably and economically, so PEF never saw the light of the day. There has been multiple efforts in the past and even now to commercialize FDCA, but all these technologies are using glucose, which is exclusively made from food sources today, to turn it into FDCA. The problem there has been the complexity of these conversions. These are highly complex processes resulting in co-product formation of challenging impurities, which has to be removed. There's usage of multiple organic solvent that you have to keep separate, recycle it. And all of that leads to low to at best moderate yield of FDCA. As a result, the cost of production has been very high and unsustainable. We at Resource are taking a totally different feedstock and a route. So the two primary feedstock that we have are waste inedible biomass and carbon dioxide. What we have at our core is a very simple process chemistry, yielding high FDCA with very high yield. There's no formation of co-product or challenging impurities, and we use water as the only solvent. So compared to the state-of-the-art glucose to FDCA technology, we cut down the number of process steps by over 70%, which is what drives down our CapEx, OpEx, and cost of production, such that we can go on to compete with also incumbent plastics. Our product PEF and its precursor FDCA have very versatile application. The two primary markets for PEF are packaging and textile, for example, your general apparel. But I do want to point out that FDCA, it's a versatile platform chemical. PEF is one of the polymer you can make out of it, but you can make a host of other different polymers, including truly biodegradable polymers out of it as well. As well as you can use FDCA by itself in cosmetics and nutraceuticals, and also as non-toxic plasticizers. So FDCA, it's a naturally occurring substance. It's produced in the human body, in a healthy human body every day. Our product has shown strong traction with our customers, and we are aiming to build on that momentum. We have validated demand with a diverse set of customers and have also achieved some really exciting manufacturing milestones. Currently, we are selling kilo quantities of customer samples. We can generate multiple kilos of material in a day with a very high purity, which is essential to make quality polymers. And this year, we are scaling the tech further. So we are building our pilot unit at this moment, which will enable us to crank out multi-ton quantities of material to finish the customer evaluation that we have started and to sign on offtake agreements. And in this journey, we've been very grateful to be supported by some incredible investors and partners along the way. So just to summarize, I'll say that the first plastics, they were invented about 100 years ago, and now consumers, governments, businesses are driving change. Our manufacturing innovation and leveraging of the pre-existing market demand is what allows us to truly reinvent this market. If we are successful, then at scale, we can reduce plastic carbon emission by at least 17%. With this, I want to thank you for your time and happy to answer any question you have.
All right, questions?
Thank you for the presentation. I'm curious actually, how have you worked on solving the challenge of feedstock around biomass?
Yeah, so the primary feedstock that we are using, it's a commodity chemical called furfural that is made from different kinds of biomass today, depending on where you're sourcing it from. So that's not a huge commodity chemical, but it's made on 500 kiloton to a megaton per year scale. So the plan is for the first 1 or 2 commercial plant, you source the furfural from suppliers, and then you turn the biomass into furfural yourself. Given that the furfural technology is 100-year-old, it's established technology, and given that you can use any kind of waste biomass that has hemicellulose in it, so that gives you a lot of flexibility in terms of your location and what kind of feedstock you can use, and that also actually makes the take very scalable. But at this point, we are not touching the biomass ourselves.
For one more question? Yeah, right up front.
How long does the packaging material take to biodegrade?
This is not a biodegradable material in the sense that, in order to be certified as biodegradable, you have to have a certain span within which it degrades. So you don't want that because you want the material to be durable. If your t-shirt is made in that, you don't want it to just degrade after one wash. But what I can tell you is that it degrades faster than that of the incumbent. So say compared to PET, this degrades much faster. So the idea there is that if accidentally it's released in the environment, it won't stay forever. But the goal with the material is to reuse and to recycle it. Those are the primary goals.
Great. Okay, thank you so much. Okay. Our next speaker is Zheng from the Greenhouse Gas Accelerator.
All right, so good afternoon, everyone. I'm Chi, a postdoc fellow at Stanford. Today, I'd like to give you a little bit advertisement on our new cement, Spark Cement. So a little bit of introduction on the traditional cement and the concrete making. So cement and concrete are the most widely used material in the world after water, but it's not so green. It takes account around like 8% of the global CO2 for making cement. So when we have a look at the cement making using traditional routine, the CO2 comes from 2 parts. The first part is coming from the raw materials part. We have limestone. The main composition is calcium carbonate. When we heat it up at around like 1000 degrees C, the limestone will decompose into CO2, release lots of like CO2 emission. The second part comes into the fossil fuel combustion. So unfortunately, hide a little bit. So the fossil fuel combustion provides you with a very strong flame and heat up all the raw material and cross-linking all the raw materials into cement. The process takes around like 10 hours, and you can assume this process takes lots of energy and also release lots of CO2. So our technology somehow considering the CO2 emission from the source, whether we can eliminate the CO2 emission during the cement producing, we are not relying on the traditional raw material, calcium carbonate. We can use concrete waste. We can use the other calcium silicate rock, and we can use some renewable electricity powered by the solar so that we can make cement very clean and very sustainable. So this is our product. We have several benefits. The first benefit is our cement particles are very small, which indicates it's very reactive. In comparison, you purchase 1 bag of cement from Costco to build your garden, you can only use several kilograms of cement to build your garden. Save a lot of cost and also save a lot of like materials. The second part is we are not relying on the CO2 material. We are not using limestone. We can use rock, we can use concrete waste, which represents this is a 0-ton carbon raw material cement. And as I mentioned, we develop a new heating method. We can make cement just within seconds instead of hours. So our method is very high energy intense, and we're melting all the raw materials, which exactly accelerates all the kinetics. The third part is our materials are so reactive, and it can be regarded as even direct air capture material. So the carbonation performance of CO2 is not so surprising. But when we evaluate the carbonation performance for our cement material, our materials has 10x higher CO2 removal capacity. So when we have a look at the traditional like heating process, fossil fuel combustion provides us with a big flame, and the flame will warm up the chamber and finally transfer the heat to our raw material. So here we develop a new method inspired by the nature, where here I named it as artificial sun. So based such a unique heating method, we can produce in cement very quickly, and our cement have very unique performance. As our students showing here, it can be used even as a Play-Doh, and afterwards it will settle down and be hardened, used as like traditional building materials. So we feel like this can explore lots of future opportunities beyond traditional building materials. For example, 3D printing, fine art printing. So as a cement engineer, we care a lot about its performance, especially, for example, the strength. So we did a very systematic experiments according to all kinds of ASTM standards. So here I just list you a little bit about the compressive strength. So the compressive strength is very comparable to the commercial cement. So when we have a look at the early strength, it even have a better strength. So currently we are partnering with Argos and Concord Cement to do our pilot demonstration. So as I mentioned, our cement is very sustainable. When we calculate the CO2 emission, traditionally, to producing 1 ton of cement clinker, we need to producing 1 ton of CO2. But our cement only producing 0.05 ton CO2, which is quite sustainable and quite remarkable environmental, would have quite a remarkable environmental impact. And we have a higher percentage of electrification percentage, which indicates we can control our process much better. And when we do the very detailed like techno-economics analysis, considering all the process from the rock ground into powder and packaging it, and our price is around like $40 to $50, which is very comparable to the current cement price. So when we compare, when we have a look at the cement market in 2023, so we feel like very excited to make big efforts in this. So lastly, I'd like to thank my PhD advisor, Professor Paulo Montero, to bring this research into scaling up, and also Professor Yi Cui from Stanford University to really bring this our technology to the market for, and also thank the fund from Sustainability Accelerator and the School of Sustainability. Yeah, thank you.
Questions for Chi?
Yeah.
When the cement goes to a construction site and is poured, what is the consistency of it at that point? Is it still like that Play-Doh, or is it more like regular?
So the Play-Doh is already mixing our cement with water. So it would have very unique like workability at the very beginning. So we feel like this performance can be used in other, for example, constructions. But the very beginning, it's just a powder material, exactly as the commercial cement here.
Other questions? Yeah.
Yeah.
Articles that are interested in this space specifically.
We reach out to some like 3D printing company and also some like concrete waste company, and they provide us some like cement waste, and they are very interested in like incorporating with us here.
Great. Okay.
Yeah,
Well,
thank you.
so much. Awesome. I think our next speaker is Kumiko Yoshinari. I think I did it better that time.
Yes, thank you.
Nutrients.
Thank you.
Okay.
Hello, my name is, as Sarah pronounced it correctly, Kumiko Yoshinari. I am at Stanford, mentor for the Tomcat Center for Sustainable Energy. But in my usual daytime hours, I'm working with 3 startup companies who are all scaling up sustainable technologies. And NovoNutrients is one of them that I'm introducing to you today. The other 2 are one is in cell cultivation of endangered seafood species like bluefin tuna, which is, as you know, seeing a lot of demand increase due to all the sushi consumption. So doing that through cell cultivation, a company called Blue Nalu. And the last one is Every, which is a company that's producing egg protein from precision fermentation. So these are all hardware companies trying to do something more sustainable, like producing protein without the animal and needing to scale up. So that's kind of my common theme. So in terms of back to NovoNutrients, what is NovoNutrients doing? It's addressing 3 major macroeconomic issues, right? One is, as we've been talking, there's way too much CO2 being emitted from industrial sources, including cement, like we just heard. The second issue is that the annual demand for protein is increasing by at least 5% per year as the world population grows, but also becomes more middle class and changing their diet from carbohydrate-based to protein. So the demand for protein is really increasing rapidly. And we're trying to feed the world population without using more water and land because, we've pretty much used up the arable land. So what is the solution? At NovoNutrients, we're using essentially the carbon dioxide from industrial sources, cement, oil and gas facilities, chemical plants, etc. And they can be impure gases containing SOx, NOx, whatever, because the process that it's feeding is a microbial fermentation process. So we've developed microbes which are very tolerant to different impurities, but the key feedstock is CO2, waste CO2 from industrial sources. So that gas, together with some hydrogen as energy source and oxygen, like any plant or any organism needs oxygen, and some minerals and ammonia that goes in to this bioreactor, which we have designed on a proprietary basis. Yes, and out comes feed food, meaning protein, single-cell protein, and some water. Because we're dealing with a lot of CO2 that can be utilized and made into valuable products, right? It's a CCU technology. We've been able to attract very large-scale industrial emitters. And I'm able to mention here Woodside Energy, which is Australia's largest energy company, producing a lot of natural gas and a lot of CO2 in the process. So that's our key investor. But then we have also traction from oil refiners, chemical companies, et cetera, based in Asia. And then on the food and feed side, we have mainly from Asia again, large aquaculture feed companies looking for a solution to feeding the salmon and the shrimp that they are farming, which also require to be fed protein. So what is the product coming out of this process? We call it Novotein, and it's basically high quality protein, which is the whole single cell organism becomes the protein, and almost 83% in most cases that we run in our lab is protein. And it has a very high amino acid profile. I won't go into the graph on the left, and highly digestible. So we've had a few trials, very successful. One is for salmonids, like trout and salmon and so forth. at an independent lab and eating this protein, this single-cell protein, as opposed to the control, which is called fish meal, which is ground-up little fish from the ocean, which is the incumbent protein source for salmon and shrimp feed, there has been superior results in terms of increased growth and so forth. Yes, I have 1 minute left. And we also did a big experiment or trial in Thailand with one of the largest aquaculture feed companies there. And they've noticed that our single-cell protein, compared to incumbent, allows reduced mortality of shrimp. And as you probably know, the shrimp die a lot in their early stages, and that's a huge economic cost. So this is my current colleagues. I'm no longer working there as a SVP for partnerships, which is the role I held for 4 years, because now I'm supporting other companies as well, but very strong background, including from other alternative protein companies and chemical companies, as you see. Just to have a quick look at what the proprietary bioreactor looks like. Yeah, it's got this loop shape. Maybe this one is even better. You see the loop? It's not like a standard vat, like a beer vat, because we need to be able to inject these gases throughout the fermentation process. But this is a fermenter. I don't think you've ever seen anything like this in terms of a fermentation vessel. So yeah, that's it. Sorry, you're running out of.
Questions for Kamika?
So in your carbon counting, do you also account for the carbon that's emitted for producing hydrogen, which is input to your
Yeah, very good question. Yeah, very good question, because as you know, unless we use green hydrogen, right? The hydrogen production process through what you call SMR can be very carbon intensive. So, our intent is really to use green hydrogen from electrolysis. And we can make the economics work only because of the high performance of our single-cell protein in terms of mortality reduction and higher growth rates and et cetera. So we have techno-economic models that show that we can use green hydrogen. And we're obviously hoping for the green hydrogen price to keep coming down as it has been. But thank you for the question.
Yeah.
Are animal feeds your main target, like output, or any other uses for the protein as well?
Yeah, the animal feed or the fish feed in particular is very high valued, and it's a high valued product. So it's a big market in of itself, and aquaculture is growing as the world population is shifting from eating a lot of meat to more and more fish and shrimp and seafood. So that's really our target market. But eventually we'd like to get into human food. But I'm personally a little bit skeptical that people will want to eat something made of, the feedstock is waste industrial gases. So, that's something. But there are other applications. We can make bioplastics, polymers. There are all kinds of other ways of using this fermentation process to make other products.
Great. Okay, thank you so much.
Great.
Okay, our next speaker is from the Greenhouse Gas Accelerator, Divya Chalise.
Hi, everyone. I am Divya Chalise. I'm a Stanford Sustainability Accelerator postdoc fellow. And today I'm going to talk about my biochar technology that I've been working for 1.5 years at Stanford. And to give you a brief introduction of the technology or give you a brief update of the status. So we are very close to exiting from Stanford now. Probably a couple of months away. And as we exit out of Stanford, this is what our founding team would look like. So me as one of the co-founders, along with my postdoc advisors, Professor Arun Majumdar, which you might know is the Dean of the School of Sustainability. And he is also the founding director of ARPA-E, along with Professor Yi Chui, who is director of the Accelerator, along with being a founder of 5 different companies. So give you a brief overview of what we are doing in terms of the technology. I first need to introduce you what is the scope of the problem that we're working with. So you might already hear about all these different sources of greenhouse emissions, such as cement, or for energy that we deal with every year. So in terms of annual CO2 emissions of all these gigaton industries, coal, oil, and gas, which are energy industries, are the biggest contributors. So coal by itself produces around 15 billion tons of CO2, and oil and gas combined produce around 5 billion tons of CO2 in addition to that. And also other greenhouse gas intensive industries like steel and cement, which produce around 5 billion tons combined. So all of these major sources of CO2 emissions can only be competed against by the only single source negative carbon technology that is at that scale, which is crops or agricultural residues. And that is because photosynthesis takes care of the CO2 reduction process, which is converting that CO2 in air to stable or to unstable carbon as glucose first and then into cellulose. So every year plants absorb around 12 billion tons of CO2 just in the crop residue, which currently being unstable goes back in the air either by combustion, by burning crop residues, or by decomposition. So every year you have an influx of 12 billion tons of CO2 equivalent in crops, but that's not being able to be stored stably as carbon. And the reason is that converting that plant waste or agricultural waste into stable carbon is really expensive. And traditionally, the process of conversion or the material that's converted is called biochar. And traditional methods of making biochar are fairly expensive. So just the processing cost is north of $100 a ton. And that is because, one, the energy input is really high. So you have operational expenses for energy, and you also lose a lot of feedstock by burning the feedstock in the biochar making process itself. And then the capital cost of the equipment is also high. What we have done at Stanford is simplified this process of stabilizing that carbon so much that we've pretty much eliminated the capital cost and also minimize the energy cost to the theoretical minimum. So now with all this, the processing cost of biochar making, regardless of the feedstock cost, is around $10 to $15 a ton, which is a 10x improvement in terms of the biochar making process. And what that has done now is that it has, compared to the feedstock cost, which we do have to pay because we're sourcing biomass, it has pretty much eliminated the processing cost. So then it brings me to this next set of discussion, which is what is the processing, or what is the feedstock cost? So currently in the US, we can get biomass at around $50 a ton. And again, depending on the source of biomass, it might vary a little. But also because we have eliminated the energy cost so much, we can go after more non-traditional sources of biomass as well, such as food waste. So in US alone, you produce theoretically around 60 million tons of food waste, and globally around 1.16 billion tons of food waste. So they are not just CO2 emitters, but big methane emitters as well. So because of our technology being so energy efficient, we can convert non-traditional food sources or high moisture sources such as anaerobic digester waste and sugarcane waste into a stable carbon. So in terms of technology, as a synopsis, we have, in our understanding, the highest yield and highest carbon retention. So theoretically, we retain almost all the carbon that's in the biomass, so nearly 100% retention, and also lowest processing cost, like I said before. And also we have very flexible feedstock, so pretty much works with any biomass that has cellulose, hemicellulose, lignin, including like agriculture and food waste. And also in terms of commercializability, not just from carbon sequestration, we can directly compete with coal now in terms of in terms of economics. So even from like energy replacement aspect, we have comparable combustion values, and also converting that into other materials such as petrochemicals through gasification. The slides are not well presented, but the synopsis is that we have done pretty thorough techno-economics, and we see the capital cost is around $3 a ton, and operational expense without the energy is around $3 as well. So where we stand right now, so at Stanford, we have a ton per day reactor, or roughly kilogram per minute throughput. The next step we are launching after the launch would be for around 6 months. We'll work on building this pilot, which would be around 50 to 100 tons per day. And that would give us one proof of scalability and also opportunity for validating our product for different applications, and also the time for establishing partnerships for either carbon removals or carbon replacement. And these are the focus markets that we're looking at. So not just within the US, but in international markets as well.
Awesome. Okay. Questions? Time for one question. Yes.
So does your process also produce a syngas like hydrolysis, and what?
No, so as I said, we have theoretically 100% carbon retention, which means that we stabilize all the carbon that is in there. So only things we are releasing is hydrogen and oxygen, and pretty much as a form of water. So there is no syngas. So we're stabilizing pretty much everything.
One more question? Yeah.
What is the current thinking on regulating the oil price?
Yeah, so we're looking at multiple markets. The easiest one right now that makes sense is carbon sequestration. But then in long term, if we're looking at bigger scales, then carbon sequestration might not work. So we're going for carbon replacement, either for like petrochemicals or replacing traditional coal itself, because the economics, it seems like in our understanding, will work for that as well.
Awesome. Okay. Thank you so much. Great. Okay, I'd like to introduce our final speaker of this session, Joshua Rabinowitz from Dioxical.
Hey everyone, my name is Josh Rabinowitz. I am the lead electrochemist at Dioxical, and I'm going to share a bit about what we are doing to decarbonize the chemical industry through the production of green ethylene. So ethylene commands a $180 billion market, and as such, it is the world's most used organic chemical. So ethylene is truly a building block, like so many of the products that we interact with in our day-to-day life. And just to give you a sense of the scope, ethylene can be converted into ethylene oxide, where it's used to make cosmetic products, glues, pesticides, pharmaceuticals. Ethylene can be converted into hydrocarbons, where it's used as fuels like jet fuel and diesel. It can be polymerized into products in packaging, textiles, medical devices. It can be converted into vinyl chloride, where it's taken to PVC, which is a ubiquitous material for construction, piping. It's used in auto parts. It can be converted into polymers used in clothing. My point is that ethylene is basically in all of the products that we interact with on a day-to-day basis. But unfortunately, the way that ethylene is currently being produced is extremely CO2 emitting. So ethylene is produced by steam cracking fossil fuels, and in this process, fossil fuels are burned to generate the process heat to drive the reaction, and they're also used as the feedstock, which ultimately ends up in the ethylene product that comes out of the steam cracker. So if you account for the process emissions associated with burning the fossil, as well as the embedded carbon that is ultimately released at the end of the ethylene-derived product's life, the yearly emissions for ethylene production is over 800 megatons of CO2 per year. At Dioxical, we are trying to turn this process on its head, and instead of producing ethylene with a process which is highly emitting, we want to utilize carbon emissions as a feedstock to produce ethylene using decarbonized electricity as the energy source. And we've estimated that the carbon impact of our process can reduce 3 to 4 tons of CO2 per ton of ethylene produced. And key to this is that the ethylene that we're making is chemically identical to the ethylene that would come out of the steam cracker, meaning that all of the products that would typically have an extremely high carbon footprint that I showed on the last slide would now have a much, much lower carbon footprint. So how do we do this? At Dioxical, we developed and optimized a carbon electrolyzer. And just to show you what that means, an electrolyzer is basically a series of plates stacked together. Between each plate, there is a catalytic core, and this catalytic core is what is actually doing the reaction where the carbon emissions are being converted into ethylene. So the carbon emissions go into the electrolyzer, ethylene comes out. And just to break this down a little bit further, each catalytic core is composed of 2 electrodes. At the bottom, there is the ethylene producing electrode, and at the top is the water conversion catalyst, where we are converting water into oxygen. A membrane separates these two electrodes, and then we apply a voltage across the two electrodes, which is the energy cost of our system. This voltage is provided by renewable electricity, but yeah, this is the main energy cost of our process. So of course, when scaling any climate solution, cost is absolutely crucial. So at DioxCycle, we're focusing on 3 key performance metrics to bring down the cost of our process. The first is voltage, which is basically how much energy you need to put into the electrolyzer to drive the reaction forward. So we've done a lot of work to minimize the voltage requirements, which of course substantially decreases our operating costs. We have done a lot of work to maximize our current density, and current density basically describes the amount of ethylene that we produce for an electrolyzer at a given capacity. So by optimizing the current density, we can use a much smaller electrolyzer, which brings down our capital cost substantially. And we've also done a lot of work to maximize the lifetime of our materials to make sure they can last for years, which is, of course, key because the less frequently you have to replace your materials, the less capital cost you have to expend to run your electrolysis process. So just to give you a little bit of a sense of the journey that we've been on over the last 4 years, in 2021, we received our seed funding round from Breakthrough Energy and Lower Carbon. At this stage, we had an electrolyzer which was about the size of a postage stamp, which could produce 1 gram per day of ethylene. Fast forward 1 year, we had an electrolyzer which is about the size of a shoebox, capable of producing 100 grams per day of ethylene. 1 more year, we had developed an electrolyzer about the size of a suitcase, which could produce 1 kilogram per day of ethylene, and at this stage that prompted our Series A from Breakthrough, Lower Carbon, Gigascale, and Lab Fund. And fast forward 1 more year to 2025. Sorry, the electrolyzer is a little bit big, but we now have an industrial scale electrolyzer, which is about the size of a car, which we need a crane to move. And this is really exciting for us because this is basically the repeatable unit, which we can stack and then parallelize in our eventual plant to make a whole lot of ethylene. So very exciting time for us. So this is kind of where we are today. We've raised $37 million over the last 4 years. And just to give you a brief sense of where we're hoping to go, in 2027, we plan to have our first commercial demo online, which would be displacing about 1 kiloton per year of CO2. And again, if we're very, very successful and are able to displace a significant amount of the CO2 emissions in the ethylene industry, that represents an 800 megatons of CO2 per year opportunity. So I'm sure the road will not be all smooth sailing, but we have a great team. Most of the team is in Paris. We have a smaller R&D lab here in the US. We are definitely hiring for our team in Paris. A lot of engineering roles available right now. So please come chat if you are interested. But yeah, happy to take any questions.
Question for Josh. So you work with your
Mhm. Mhm.
What is ethical when you're fighting for like develop
It's a great question. I can't share too much about the specifics of our MEA, but it's been a lot of both conditions and catalyst optimization to get there. But yeah, I unfortunately can't share too many details about our MEA. It's obviously proprietary, but I can maybe chat more about it offline if you're interested.
Okay. All right. Well, thank you so much, Josh.
Thanks a lot.
And let's take a moment and thank all of our presenters. I didn't mention, but all of the presentations today either are current students, former students, or somehow the technology was born in a lab here on campus somewhere. So everything had a Stanford kind of affiliation, which is just great to see. So thanks again for attending, and I hope you have a great rest of your day.